Hello dear students. In previous two lectures, we were discussing about the nervous system, neuron, then we have studied how two neurons communicate. In that we have covered resting potential, action potential, and what is the use of sodium potassium pump. And now further we will discuss about the electrical analog for neuron, means how a neuron can be represented by an electrical equivalent circuit. So a neuron can be represented as an electrical equivalent circuit, that is a mathematical model which represents all the major electrical properties of a given neuron. We know a neuron equivalent circuit as all the other electrical equivalent circuits include batteries, capacitors and resistors. Similarly, a neuron equivalent circuit is also made up of batteries, capacitors and resistors. Let's first talk about the capacitance. What is a capacitance? Capacitance is the ability of an insulator to separate electric charge on either side of it. Also, it is the ability to store charge. So, in a neuron, how you can say that neuron have a capacitance? So, in neuron, the cell membrane, which is a lipid bilayer, gives a membrane capacitance. As you can see in the diagram, that cell membrane is nothing but we can categorize it to be equivalent to a capacitor. The membrane, though, it is a leaky capacitor because it has ion channels. As we have studied in the last lectures, that there are some ion channels like sodium ion channel, potassium ion channel, fluoride and ion channel, which provides it the conductance and also the ability to generate an electromotive force. So, a source of electrical potential is known as the electromotive force, that is EMF. And an electromotive force generated by a chemical potential difference, we call it as a battery. So in neurons, the difference in concentration of ions across the cell membrane, it contributes to the EMF, that is electromotive force. So we can say that difference in ion concentrations, mainly we can say it is equivalent to nothing but batteries. Further, resistors are ion channels. They can be symbolized or they can be categorized as the ion channels that allow ions to move through the membrane. So, by combining all these components, the equivalent circuit for a passive neuron can be obtained like this. As you can see in this graph, you have in this figure a capacitor, which is nothing but a membrane, R representing the ion channel, and again this E represents the potential which is at rest, basically resting potential. And if we have the movement of ions, that means some resistance will be there and that will contribute to the membrane potential, that is Vm. Now let's obtain the equations governing this circuit. So as we know that charge is nothing but capacitance into voltage. So here charge is basically difference in charge. C is, we can say, capacitance, which is constant because it is related to insulating properties of the membrane. As in the neuron, we have seen that cell membrane contributes as a capacitance. And Vm here is the membrane potential, which is basically the difference between the potential inside and outside. So we are taking it as Vm. Now, first equation we have based on this charge. We know in equation number 1, as you can see, that current is nothing but the rate of change of charge. So if we differentiate this Q is equal to CVM equation, you will get the equation of current across the capacitor, that is equation number 1, which is IC is equal to C dVm by dt. That means we have differentiated with respect to time. Now if I want to calculate the equation of current across the resistor, so we have to use Ohm's law, and from that you will get the equation number 2, which is IR is equal to, we can say, Vm minus EE. Again I am telling it is the resting potential, so divided by R, you will get the equation for current across this resistor. Now due to the conservation of law of current, we have the total current, or I can say current entering or leaving at a particular junction should be 0, that is Kirchhoff's current law. So by that we have IC plus IR, that is capacitive current, and the resistive current. The sum should be 0. Now using the previous equations number 1 and 2, you will get this equation C dVm by dt plus Vm minus C whole divided by R, that is equal to 0. Means we are keeping the equation for capacitive current and the resistive current. Now a little bit manipulation if you do for this equation, and then we can assume that tau, which is nothing but time constant, equal to RC, you can get equation number 3, and you can keep the value of tau, and then finally you will get the equation tau dVm by dt is nothing but the difference of potential. E is resting potential and Vm is the potential across the membrane when we have some movement of ions. Now neuron, further it can be represented by Hodgkin-Huxley model, that is a little bit more in detail. We can have a equivalent circuit. In that it is including the channels as well. You can see this is a kind of passive circuit which we have seen in last slide, and these are the voltage dependent channels. We have included the sodium channel and the potassium channel. We can also have chloride channel in this. Here we have used G, that is nothing but reciprocal of R, we can say conductance, just to simplify the equations, as you will see in the coming slides. Now from this, again from the circuit, we can get the overall equation, that is the total current flowing across the cell membrane is the sum of, again, the capacitive current and the ionic current. And further, the ionic current includes the sodium ion current, potassium ion current, and the current across the resistor, which we are considering as the leaky current. So we have ionic currents and we have the leaky current. As I mentioned, G here is nothing but 1 by R, that is reciprocal of R, and it is known as conductance because we are taking equation in terms of I. So because we know I is nothing but V by R, so we can keep in equation it is G into V. So just to simplify the equation, we have taken this G, or I can say conductance rather than resistance. Now, according to conservation of current law, or I can say Kirchhoff's current law, overall current again it needs to be summed to 0. That means again the sum of capacitive current and the ionic current, which also includes the leaky current, it should be 0. Now keeping this, all the values which we have seen, we have to keep in the equation, and after keeping you will get this equation, that is capacitive current is nothing but equal to the sum of ionic currents and the leaky current. So Cm dV by dt, it is the capacitive current, and this Gna, that is conductance across this sodium ion channel, Ena, which is the resting potential contributing for sodium ion, and V is the membrane potential when we total, we can say net membrane potential across the membrane. Similarly, the equation for potassium ion current and the leaky current. Now further, if we assume that some current is injected from the current source. Then again, the overall equation will become IC plus II, that is sum of the capacitive current and the ionic current, and we have the injected current, that is equal to 0. Now you can ask why we have taken the sign negative. It can be positive, it can be negative. The reason for negative means if it is decreasing the potential, then we are making it as negative, and if it will increase the potential across the membrane, we can keep it as positive. So here we have taken the negative sign. So again, by keeping the values, we can say that again we can say like capacitive current is nothing but the sum of all the other currents by using again the conservation of current law or the Kirchhoff's current law. So capacitive current is nothing but equal to the sum of ionic current and the injected current. So this was all in this lecture, and this was all about this topic, which is basics of neurology. In that we have covered the nervous system, the neurons, the communication among neurons, and then this equivalent model for a neuron, or we can say electrical analog circuit for neuron. So for now, thank you.